Okay, so okay. So neural machine translation is, we are going to do this sequence to sequence architecture, and for sequence to sequence architecture, encoder decoder networks, it requires 2 RNNs. This is what we are doing. I mean, most of the time, many neural network ideas seems funny and nonsense. That's how they seem, but for some reason they work. And this sequence-to-sequence model or decoder-encoder stuff works. It works very well, especially if you do the necessary adjustments. This is what you do, okay? I feed this French sentence to an RNN, okay? And at the end, I get my internal state or cell state or hidden state, whatever you like to call. Let's say it's an RNN, it is the hidden state. I feed that hidden state as H0 to my RNN, encoding RNN, and I train that network that way. And I say that, okay, when I give you a start, you should produce me an he. Then when I give you an he, you should give me an hit. If I give you an hit, you should give me an me, and etc. But the thing is, this is my blue, okay? This is my encoding RNN. I am encoding data into a vector, that contains all the information about this sentence. I am encoding all these words in a vector only. It's the encoding state. Okay, this is decoding state. Then I am encoding whatever decoded inside this vector. Okay, so encoder and decoder. And how am I going to train this? I'm going to train this. My losses will be defined on this one. I should produce a he, okay? Then I should produce a hit, then me. So I take the loss functions, loss values, and I take their gradients with respect to all the weights up until these words. Okay? So there is a back propagation going on in there. So I am training 2 networks, an encoder network and a decoder network. Okay? So why don't we use this our previous structure of this, okay? If these are my weights, the steps, time steps, if I do this, I go to school early, ben okula erken giderim. Previously we do this, right? End to end, okay? Why don't we use this kind of structure, this kind of architecture for the machine translation problem? The answer is obvious. What is the answer?
Sequences are not the same. First, okul came first, and second go came first.
Yeah, well, it is not the same order, yeah, right? The sequences are, I doesn't have to correspond to Ben, okay? Go doesn't have to correspond to okul, right? And the number of words are different, right? Number of words are different. Their sequences are different. And the thing is that, remember, this is RNN, right? Okay? This is RNN, and inside the RNN, I produce this one, and then this one, then this one. So I take my input and I produce my result immediately. This is not a good architecture for the translation. So my translation is, I take the complete sentence in and I produce a complete sentence out. That's why I need to do encoder decoder. Encoding network it kind of captures all the meaning, all the syntax, all the semantics of this sentence in a hidden state vector. Then I input that hidden state vector to this decoder RNN, and this decoder RNN is going to produce all these words one by one. Okay, so that's what's called encoder decoder network, and it works up to some degree, of course. Nicely, it is better than statistical machine translation. Okay, maybe I should ask you this: what do you think the main problem with this kind of approach is? What could go wrong?
It may lose the long-term context of a paragraph or a long paper.
Oh, you mean that this is only a sentence and this is another sentence?
Yes.
So I might say that, well, why don't we input a complete paragraph and ask it to produce another complete paragraph? So you are saying that whatever I have translated as a sentence, I forget about it. This one doesn't. Yeah. Well, then translate it by paragraph, maybe I can say.
This encoding vector may be small to keep all the information.
I think you're trying to say this. This is our bottleneck. This is our bottleneck. Here, all the information inside this sentence has to be stored inside this vector, which is our hidden state, right? Our hidden state is like 200-dimensional vector, that's it. Well, I can make it 200-dimensional, but again, it's a small vector. If I make it larger, I am using many more parameters, right? Well, if I am using many more parameters, then there is this problem of overfit and that kind of stuff, and etc. So this is the bottleneck problem here. You need I mean, the communication between encoding network and decoding network is through this single vector, and that's going to cause some problem. Okay. And sequence to sequence, we are going to solve that problem using attention. Well, we never solve any problems in deep learning, actually. I never heard that we solved that problem. We addressed it, 98% we solved it, and sometimes we realize that, well, that's not a problem, actually. That's what we want kind of approaches. So we are going to address that problem up to some degree. So sequence to sequence architectures are very popular. We use it in many places. For example, the summarization. I gave the whole paragraph here. I get the summary out. That's the sequence to sequence. Dialogue. I ask the question, I get the answer back. I use it in that case. Parsing, it is important too. I give the input text. My output text is the parsed words, okay? This is verb, this is noun, this is an adjective. And code generation, I do that too. Code generation, I give the natural language and it produces the Python code, right? I do that. I think last year or 2 years ago, one of our senior students, fourth-year students, undergrad program, she took the Python code and she produced the command lines for it, for the command line, and later we did that this is useless. I mean, why are we producing command lines for the Python code? I mean, command lines are supposed to be written by the people, right, by the programmer. I mean, if I don't write it, then that means there is something wrong. Then she came up with this idea. We input the natural language for the command and Python code at the same time, and she said that, okay, this is a good enough code for this. This is a good enough command for this code, or not good enough command for this code, kind of thing. So it is expecting both of them from the programmer. Anyways, okay, these are all using sequence to sequence architectures. And for the translation, we are going to use that too, okay? Sequence to sequence model is an example of conditional language model, okay? What do we mean by that? Okay, given this x, what is the probability of y? And optimize this y, okay? and that's one thing. The other thing is that how am I gonna train such a neural machine translation system? The nice thing is I don't have to give the alignment, right? This is my input sentence, this is the output sentence. This could be a 4-word sentence, this could be a 50-word sentence. I don't have to produce the alignment. Very, very nice. It's just input sentence and output sentence. That's it. That's it. Okay, and that's what's happening. Encoding network, decoding network. I measure my negative log probability of these words and I add them up. This is my loss, okay? In order to decrease this loss to a lower value, take the derivative of this loss with respect to all these parameters one by one, right? And change those parameters so that your loss is smaller. Okay? Typical back propagation. The thing is that I have two sets of feeds, encoder network and decoder network. Okay? So training again, there is a problem with the vanishing gradients, because if you look at this path, okay, it is going all the way back. Many gates I have to go through, but using LSTMs maybe I can handle it. But this problem here, the bottleneck will exist. I have to go through that bottleneck. Whatever information I am flowing, it will be through that vector. That's going to be a problem, and attention is going to solve that problem. Okay, so let's say I have somehow successfully trained such a network. Okay, I have successfully trained such a network. Then when I am using this in real time, in the real world, I will input this, okay? I will do this, okay? I will give this he at the beginning, okay? Okay, this is one, okay. I input this to the encoding part, this part. I get the vector out. Now for the decoding part, I say start. It produces an he, okay? It produces an he. Then I give he as an input, it produces a hit. I give a hit, it produces an A. I give an A and it's going, okay? So whatever it gives me, I have to take it, okay? Whatever it gives me, I have to take it. It doesn't look like I am measuring some kind of a probability, right? It is just giving me one output, and I am taking that output and I'm saying that this is the most probable one. How about the second probable or third probable one? Well, maybe for that we can use, okay, we can say that at every step, it said that for the first one, he is the most probable one, right? Out of 40,000 words, he is the most probable one. What is the second most probable one? She, maybe. What is the third? Maybe they, etc. I don't know. If I try to feed that information to a search algorithm, if I try to exhaustively try to see what kind of possibilities all I am getting, it's going to take lots of time. Well, since it's exhaustive, it's going to be exponential. It is not too expensive, it is impossible, it is intractable, right? V to the power t. T is the number of words, etc. But if I keep only 4 or 5 most possible, most likely solutions, we are going to call it beam search decoding. Beam search does this, okay? That's a very generic search algorithm. Don't go greedy, okay, being greedy is okay because it is very efficient. But being greedy is greedy, we know that, that's not good. So let's be greedy, but at least keep k most probable partial translations, which we call hypotheses, okay? So this is what we are going to do. We will we will keep k most probable partial translations for the first word, since I am taking these out of a softmax function. Softmax assigns a probability to each of the candidate words. I can pick the top k most probable words at the beginning, but how about the second one and the third one, etc.? This is what we are going to do. If k is 2, let's say we are going to look at only the first two most probable ones. From the start, okay, I get two probabilities. One of them is, okay, he, the second one is I, okay, he and I am keeping these two. And if I feed a he to the network, it's going to give me another one. If I keep an I, it's going to give me another one. So what? I feed he, okay, it gave me hit back or struck back. If I give I get a was or got, okay? So most probable ones are, okay, these are my negative log likelihood stuff. Remember, small is better. It's going to choose hit and was, okay? This one and this one. We are trying to optimize it. So I will ignore these two, hit and was. I ignore the struck and got because k is 2. Now I am feeding hit, it's going to give me 2. I am feeding was, it's going to give me 2. And I will do the same thing again. I will ignore again 2 of them. So it looks like I am going to switch to this branch now. So if I do this by keeping k2, I will have 2 most probable solutions in my end. Am I doing something exhaustively? Of course not. Again, this is greedy, but it is not as greedy as choosing the greediest solution. At least I am choosing the top 2 greediest solutions in my hand. Okay, that's the beam search, and at the end I am going to get 2 sentences, and this, it looks like it is choosing the same path. I am not continuing from the other path because this has got stuck somewhere. Okay. So beam search is something like that. The stopping criterion is until we reach the time step t, okay, or we have at least n completed hypotheses. Okay, that's one thing. So neural machine translation is better performance, more fluent sentences, better use of context, better use of phrase similarities, okay. It has many advantages compared to those statistical machine translation. And this one is important too, end-to-end. Remember, with the statistical machine translation, we write stuff like P given X, what is my alignment and Y, right? Alignment is a completely different problem. We separated it out. Okay, so since you separated out the alignment, it becomes another problem easier to deal with, but you are not solving the whole translation problem at the same time. You are dividing into 2, and solutions are found differently. That's not end-to-end. This single neural network optimizes end-to-end. From one end, my input, from the other end, from my output. I am learning everything at the same time. Okay, no subcomponents to be individually optimized. This one says that I am going to find the language model, I am going to find the translation model, I am going to find the alignment model, 3 of them. And they are independent of each other. I am optimizing them that way. Okay, and this is very important. It requires less human engineering effort, because all I do is just corresponding sentences, parallel sentences, that's it, no alignment, okay, required, no labeling is required. Same method for all language pairs. That's why whoever is doing the machine translation work, they don't need to know the languages actually. Okay, good. Disadvantage, what is the disadvantage? Yeah. Neural machine translation is less interpretable. Hard to debug. I don't know what's going on. Okay. I cannot say, when you see that kind of a sentence, translate it this way. Okay, I know this is the solution, but I don't know how to say it to this neural machine translation. And safety concerns, well, we are going to see what that is. Let me show you some examples. Let me show you some examples about, yeah, problems. Do you understand the problem here? My friend has no hair on the tongue. Well, it's from Spanish to English. It looks like there is a phrase in Spanish. Dilin kemiği yoktur. Dilin kemiği yoktur. Ağzında bakla ıslanmaz. Bu öyle mi? Ağzında bakla ıslanmaz mı bu? Ne bu? Nedir sizce bunun şeyisi? Türkçesi? My friend has no hair on the tongue. Bence dilin kemiği yoktur. Dilin hiç kemiği yok. Ağzını tutmasını bilmiyor. Ha? Öyle bir şey. Well, if you try to translate those kind of stuff, this kind of funny stuff happens. I understand. How about this one? From Hindi to English, when Shyam came to know that he failed the exam, his face went down. Well, for Turkish it is okay, it is acceptable. For English it is funny about it. Yeah. This is something, idioms, phrases, known stuff. We don't know how to integrate these kind of idioms into the language, into the neural model. Either you're going to say that if you say this one, it is translated this way, or you are going to give lots of examples about that. Okay. How about this one? This is important. It happens between Turkish and English like that. Okay. If the source language doesn't have any gender distinction, okay, like Turkish, we don't say he or she, we always say o, right? In Turkish we can say o bir hemşiredir, o bir programcıdır. How do you translate it to English? When you say o, you have to say either she or he, right? So this is biased towards nurses are females, programmers are males, right? So not acceptable. So how am I going to translate this then? I mean, it depends on the context, of course. So we need to deal with this kind of problems too, okay? So definitely, why is this happening? Because this one read as an input lots of sentences about nurses being females, right? That's why it is producing she works as a nurse, right? This one is the most funniest one. This is real, right? If you, yeah, it works. I mean, why does it work? Remember your homework? Your third homework, it is talking about the syllables, having a word vector, the syllable vectors. If you put together lots of syllables together, it makes another vector. Okay, it's a word, right? So the system thinks that, well, these are the words maybe I don't know the meaning of, but I produce the word vectors. Word vectors are most closest to that one, and if I translate it, it comes this one as the name of the Lord. Well, the thing is that it is grammatically correct, and for some people it may make sense, especially if you don't understand it. You might think that it is correct. Okay, uninterpretable. What?
Even if input is senseless,
yeah,
it is trying to make sense.
Yeah, exactly. I mean, that's what the Google Translate does, right? Because it converts all the words to some kind of a word vector, right? And our fast text or the BERT or those kind of stuff, they can assign vectors to even the nonsense stuff, and I can translate them. And let's try one. I don't know what translate. Am I connected to internet? Kind of, maybe, no. Well, you try it yourself. You say, ben kitap okudum, is going to say, kitap okumayı severim, is going to say, I like reading books. Ben ABC okumayı severim. It's going to translate to something, I don't know what it's going to translate to say. I cannot test it right now because my connection is, let's switch to this one. Oh, I know the problem. The problem is I did not do this yet. Okay, translate. I like to read books, and if I do this, it says ABC. How about kebab? Kebabs? It thinks that it's something. Oh, did you mean this? Okay. Some Persian word. Matbook. What is matbook? Matbook şey mi demek ya? Matbook mektup gibi mi? Macbook okumayı severim. Matbook'un bir manası olsa gerek. Bir dakika. Matbook. Bir bulalım mı arkadaşlar onu? Yok. Matbook diye bir şey yok ya.
Mektup olarak algılayıp
Düzeltti sizi.
Mektup ama matbook'la mektubun ne alakası var ya? No, well I think it says that, where is it? Yeah, where is, okay. I don't think that it knows matbook. No, well this one doesn't say, did you mean ben mektup okumayı severim? I think it is mektup nece? Farsça mı Arapça mı?
mektup Farsça Arapça.
Hocam Özbekçe.
Özbekçe mi?
Yani dil algıladı ilk mektup yazdım Özbekçe çıktı.
Neymiş? Not mu?
Notebook. Notebook dedi İngilizce çevirisine.
O da mektuptan geliyor.
Ama letters dedi burada. Anyways, so it assigns a word vector to this thing, and it is letters, so it translates it that way. We cannot make sense out of it. That's the point, right? Okay, it is not. In this case, it is acceptable. Sometimes it produces something very, very unacceptable, socially, politically wrong, and sometimes it puts Google in a very, very tough situation, saying that your translator is racist. It is calling me this and this, right? So we never have this kind of problem with the engrams, right?
Sometimes people also manipulate training data.
Yeah.
Put some,
That's what happens with the Facebook stuff, right? They talk to Facebook's chatbot for days, and they told it how to be a racist, and they told it to be, well, yeah, well, that was not funny, but it was funny that Facebook thought that it's going to be trained in nicely. Okay, so, yeah.
Does the model know that it is generating something meaningless? For example, in that idiom of Spanish, does the model know that it's generated a sentence in English, but it is not a sentence? That
Well, the thing is that, well, it always produces something grammatical, right?
Yes.
But it also assumes that the input is meaningful too. Since I am a human being, I am asking this, translate this, okay? It doesn't say what you're saying is not meaningful. It doesn't say what you're saying is nonsense. I am going to translate it as we entered it. Maybe you want to do this, maybe you don't. It's like this one, okay? If you entered your text as this AG, well, I'm going to translate it. So the output is always grammatical, and it makes some sense to some degree, okay? It doesn't produce this kind of stuff. But it used to produce it, nowadays it doesn't. Okay, because remember, this one is like P x y times py, right? Py is the language model. So whatever I am producing has a high probability, right? Both syntactically and semantically. So this is given. So this is the corresponding thing. Do they correspond to each other? Well, this is the best I can do in terms of corresponding it. So this one doesn't say anything like, this is not Irish, this is not Spanish, okay? I will pick a sentence that will maximize this one. It is a smooth reading sentence, and this is the best P that I can find. That's what it says. Okay, so we talked about these. Yeah. How do we measure the success of our translation? It is bilingual evaluation under study. It uses n-grams, okay? This is my input sentence and this is the output sentence. First, it looks at the 1 grams. How many same words are there? How many 2 grams overlap? How many 3 grams overlap? And how many 4 grams overlap? Okay, so that's one thing. The other thing is that plus a penalty for 2 short system translations. Okay, it is useful but imperfect. Well, we don't have any definition of the perfect translation anyway. Okay, so we still use it. It is not because we use it is perfect. We use it because it is accepted. Everybody is measuring their performance using the blue score. These are the blue scores. Okay, a blue score of 30, 35, 40 are very good. Okay, we talked about this. So is machine translation solved? No. Okay. Out of vocabulary words is a problem, like the one that I told you a few minutes ago. I made up a word, I tried to sound like an Arabic word, and it really felt like an Arabic word, that one too. Say that it was, I think that what I had in mind, what I had in mind is like something like mektep, kitab, something like that, but it came back something close, right? That was not bad, but it could have been a disaster. Okay, the domain mismatch between the train and test data, we talked about it. Context over longer text and low resource language pairs. Turkish is not a low resource language pairs, but there are some languages where not many parallel corpora is available. Okay, we talked about this. We talked about this, and we talked about this. Okay, let's look at this idea of attention. Bottleneck. How am I going to solve this problem? Maybe you guessed it. We are going to find connections between those. But how am I going to connect, okay, this with, okay, how am I going to connect this pi with this one? How am I going to connect, well, I don't know the rest. What is this? Is this me? Maybe, I don't know. I mean, so, well, I am not going to use the dictionary. This is what I am going to do. This is what I am going to do. Okay. Don't raise it. Okay. At this point, when I say start, I have an internal state, right? I will compare my internal state. The internal state is a vector, right? 100-dimensional vector. I will compare this 100-dimensional vector with this one, this one, this one, and this one. Okay? I'm not trying to find the closest one. I'm just comparing them. How do you compare two vectors? you just take the dot product of them, right? Multiply these two together. It's going to give you the cosine of the angle between these two vectors, right? So it will produce, okay, an attention score here, one number, an attention score here, another number, attention score, another number, attention score, another number. So when I am producing a word, my attention is most likely on one of these words, and that word has to produce a large number, dot product. Okay, so this is actually a new data for me. I measured my similarity with all the internal states of my encoder network. Okay, so that's going to be, so it looks like start is definitely related with this one. The rest of them are not that much. So this is a vector. I will get that vector, attention output, and I will put that attention vector on top of my internal state, and my new network will produce he using these two vectors. Okay, I produce then he. And for the second one, I am going to do the same thing again. Okay, I will produce a hit, and I am going to do the same thing again. Compare this with all of them here, and I am producing me, right? So what I am doing is, I am not depending only on this bottleneck vector anymore. Every time I produce something, I am communicating with the inputs, right? And I am getting this vector and I am producing the output. Okay, this is called attention. When I am producing this word, where is my attention on the original sentence? Okay, where is my attention on the original sentence? I get that and I put that into, I put that into my output. Okay, so this is my training, how it is done. When the time comes to runtime, okay, I put this in, okay, I put the start out, I compare it with all of my input words, okay, that's going to give me an attention, and that's going to give me a word, right? Okay, so that's how it works, attention. Okay, that's how it works. I'm not going to talk about this. And the thing is that attention will give us this alignment matrix for free, right? And the nice thing is, see this one? This is much better than the alignment that I'm trying to find. Why? Remember the alignment that I was trying to find? It was a binary matrix, right? Is this a binary matrix? Orhan hocam sen misin o ya? Orhan hoca mı geçti orada? Orhan hocayı tanıyan var mı? Sen tanımıyor musun Orhan hocayı? While you are talking about this, previously my alignment was, where is my alignment? Let me find the alignment. Yeah, here it is. 77. Well, no, I'm trying to find that exactly. Yeah, this one. Yeah. See? It's a binary network, 1 or 0, right? How about this one? 72. Yeah, this is not binary. Much better. This one and this one are kind of loosely related. This one and this one is loosely related, but these are definitely very related. And I cannot see how gray. I think this is grayer than this one. Which one is grayer? Anyways, okay. Let me call Orhan Hoca'yı bir arayayım da ya, onun şeyi bende kalmıştı. MIT. So, very surprising result. Alignment is for free and it is better than. Hocam senin şey bende ya.
Çok teşekkürler. Ben de zaten şimdi buradayım. Erkan Hoca'nın yanındayım.
Aşağı gelirsen verin, ben hemen bir toplantım var, çıkmak zorundayım.
Hemen geliyorum hocam. Hemen geliyorum.
Tamam, görüşürüz. So alignment is for free. Okay, I got the alignment. When am I gonna use that alignment? For debugging maybe, right? For debugging maybe. Okay, it is producing this because it thinks that this word corresponds to this one. Okay, it definitely improves the neural machine translation performance. It solves the, well, it solves, in quotes, bottleneck problem, it addresses it. Okay, helps with the vanishing gradient problem. Birazdan 3 dakika, 2 dakika, 1 dakika. Vanishing gradient problem and provides some interpretability because alignment is for free. Okay, I never did this before, right? I never did this before. I didn't give it as an input, but it figures that out. It's kind of unbelievable. Nobody thought that we can do such kind of stuff by just giving the corresponding sentences, but it really works. These are not science fiction stuff. As I said before, top NLP researchers of like 15, 20 years ago, if I told them, if I give them the same lecture that I'm giving you right now, nobody would have believed me, including myself. But believe me, it works. These are real. Why are you looking at me like that? Just read that it really works. These are not my slides anyway. Okay. Okay. Attention is a general deep learning technique. Okay. After they realized that attention works very well, okay, somebody came up with the idea and they say that, okay, if attention works that way, why don't we use attention all over? I mean, why are we using this RNN or LSTM thing? Okay, you always take the attention between the words and keep using it all the time. And it turns out that that idea is not that crazy. Transformers are doing that, okay? Transformers are using attention all over, okay? So some people say that, okay, some people say that since I am doing this attention, all we are doing in the neural machine translation or neural machine learning world is multiplying vectors with vectors. So the important thing is that finding in which order to multiply what vector with what vector. If you find that order, the numbers are going to be better. Doesn't matter if you think that it's a neural network or not. So all you do is just multiply and add numbers and pass it through a sigmoid function. And if the results are good, then use it. You don't have to explain anything, okay? That's what the world comes to nowadays. Okay, at the end of this chapter, attention variance, we talk about it. Several attention variants, and we talk about that too. Okay, we took this, yeah. So next lecture, I am going to talk about this transformer thing, okay, which replaced the this employment of attention, and we'll talk about the BERT kind of stuff or the GPT kind of stuff, which is the most widely used neural language models. Attendance verdim ya. Ne yaptın? Uyudun mu sen? Geç mi geldin? İlk ders gelmedin mi? Tamam, gel hemen imza al.